All right, everyone, we're back to bivariate statistics. This is the second in the series. This time we're going to go over some cross-tabulation tables and their associated measures of association. Before the break, we did talk about, before the break and after the midterm, we talked about some crosstab tables, but in very, very general terms. So, the last time we met, we quickly talked about cross-tabulation table rules. Actually, I think we spent quite a bit of time on that. The nature of putting together 2x2 tables, some basic rules about titles and where the dependent variable goes, all of that sort of stuff. So this time we're building off of those cross-tabulation tables. As I mentioned before we went to break, I quickly went over some of the tests that could be conducted using those crosstabs tables. The intent of those tests is to try to determine whether or not there's an association between one variable and the other, your independent variable, or x, and your dependent variable. Oops, what happened? Hold on. Sorry about that. The key to cross-tabulation tables is that first you must make sure that what you're using is some sort of combination of categorical data. Okay, so your independent variable and your dependent variable are measured in categorical terms. That means, unlike a test of means, which we spoke about before, we are talking about variables that are measured as nominal or ordinal. This is often the case for survey questions. For instance, if you've got a Likert scale that you're working on, or if you're asking people whether or not they approve or disapprove of particular policies or issues, things along those lines. Those are nominal or ordinal questions that you're seeking to analyze. Now, what happens when you aggregate the results from those questions is you'll get numbers, right? You'll get percentages. Numbers indicate the percentage of people or the raw number of people who fall in one category, who believe they approve or disapprove of some topic or fall within one of those Likert scale categories. Okay, again, so remember the variable is measured in a categorical way, nominal or ordinal, but they are then aggregated so that you can produce tables that indicate just how many people responded to those distinct categories. So there's a whole mess of tests that we could talk about here. And this table was a table that I promised you before we went to break. I will also put it up separately as a document on Blue Line. It basically summarizes these tests that we will talk about or have talked about so far. So we talked about t-tests last time. We will talk about f-tests later. This time we're going to talk about the gammas and lambdas in this particular table. Don't worry, you'll see this table again. As you can see, what the table summarizes is gives you a quick summary of what these different tests tell us. So a t-test, as you recall, is a difference between two means. An f-test is when you're looking at multiple means. A chi-square test, which we'll talk about next, is a difference between observed and expected frequencies. It provides a test of independence. Proportional reduction in error tests like phi, gamma, and lambda are measures of association for 2x2 tables, right? Cross-tabulation tables. As you'll notice here, the phi test uses nominal variables, the gamma uses ordinal variables, and lambda requires that at least one of those variables be nominal. What's required for all three of these tests, these proportional reduction of error tests, we're looking at cross-tabulation tables 2x2. Right? The difference between these different measures of association is that, for instance, a phi will give you a number that indicates strength and direction of the relationship, ranging from -1, indicating a negative relationship, to +1, indicating positive, and again, with the higher values indicating a strong association between the two variables of interest. The gamma test will be very similar to the previous test we just talked about. Again, -1 to 1, indicating strength and direction of the relationship. Lambda, on the other hand, provides an indication of the strength of relationship between the two variables without indicating whether or not they are positive or negative. Okay. These tests, the proportional reduction and error tests that we're talking about today, focus on making comparisons across a table like the one you see here, and trying to identify concordant, discordant, and tied pairs. So, what is a concordant pair? A concordant pair is where one case is higher on both variables than the other case. So high x and y compared to another case. In this case, Hera is concordant with Dawn. All right, so one is got a higher x and y compared to another case. A discordant pair, on the other hand, is where one case is lower on one of the variables but higher on the other. The basic thing about a discordant pair is that you're violating the expectation that as one variable increases, so does the other. Okay, so you might have a high x and a low y. In this case, Carl, which is very high on the x value but low on the y, is discordant with Ernesto, who is at a medium x, medium y, Gus, and Dawn. Okay. Finally, tied pairs is where one case is like another. They may both have the same value on both variables, high x and high y, for instance, or low x and low y. In this case, low x and low y, the perfect example is Ike and Jasmine, who coincidentally happen to be in the same cell. The gamma tests, just like the lambda and the phi, are all focusing on a comparison of these concordant, discordant, and in some cases tied pairs. The formulas are located here. You've got the formulas in your book. I'm really not going to spend any time on this. They are, to the extent that you should know that they exist, that they require specific types of variables, and that they produce specific outcomes, how to read them. That's really all that I'm going to expect of you from here. I'm not going to expect you to have these formulas, nor are we going to walk through them. In large part because there are some pretty serious limitations to these tests. First of all, I mean, we kind of mentioned this in the previous slide, they're limited to this particular type of size of cross-tabulation tables. They tend to be fairly small, with the exception of tau Cs. They don't use all of the information available to us. They're really just looking at whether or not these different items falling inside these cells match on some level. So they use pairs, but they're not actually counting the number of the cases, not the values of the cases. So there's a lot that's, still missing in this particular in this series of tests. They exist. You should know what they are briefly. You should be able to tell me what the outcome would indicate to you, but in reality, you probably won't have too much need for either of these tests. Why? Well, while there are benefits to these tests, the one test that tends to fit the bill best, in other words, is more flexible with the size of the table and more flexible with the type of information that you include in it, that would be the chi-square test. Among other things, it tries to take in as much information as possible, not just looking at pairs. It also takes into consideration some other factors, which is why we will turn to the chi-squared table next. All right, stay tuned for the next one.